It's my pleasure to introduce Professor Martin Virial from Oxford. I got to know Martin back in the late 20th century when doing his PhD with Ken Freeman at Stromlo while I was a PhD student at Melbourne. Those ASA and Harley Winter School connections endure over the decades. At the time, Martin was working on boxy peanut galaxies, so very interested in the bulges and the bars within the centers of spiral galaxies. Since that time, he has moved on to a number of places, a postdoc at Leiden, a Hubble Fellowship at Columbia, and has really broadened his interests to looking at galaxies across a range of scales, supermassive black holes, molecular clouds, still a little bit of interest in galaxy morphologies as well, and broadening wavelength coverage as well, including the use of ALMA to study this variety of objects. So I'm very much looking forward to today's talk, which is moving down from galaxies down to giant molecular clouds and star formation. Martin, when you're ready, take it away.
Thank you. Thanks very much for having me. It's a pleasure to be back in Australia after being away for way too long. And of course, not traveling much like I guess most of you over the last few years because of COVID. So it's nice to talk in person with people and catch up over a drink or a meal. So as Michael said, I'd like to tell you today about kind of my latest, I guess, metamorphosis. I like to reinvent myself, switch topics every, I don't know, 6-7 years. So that's my latest pet topic, is looking at the interstellar medium galaxies at very high angular resolution and therefore spatial resolution, given that I'm going to be looking at quite nearby objects. And I want to talk about the project called WISDOM, which stands for Millimeter Wave Interferometric Survey of Dark Object Masses. And for once, it does exactly what it says on the tin. This is a project that's really designed to measure the masses of the supermassive black holes lurking at galaxy centers using high resolution observation of the molecular gas. So essentially all the galaxies that I'll talk about are galaxies where we've tried and typically succeeded to measure the black hole mass using the data I'm going to show. However, what we didn't really plan or didn't fully appreciate at the beginning is that the same data allow us to study in a spatially resolved way the molecular clouds in those galaxies. So essentially the stellar nurseries, where star formation takes place. Just because the data are such high angular resolution, we can do that for free. So now about half of the team is actually working on giant molecular clouds or GMCs rather than supermassive black holes. So that's the team, and the people in gold are essentially the people involved in the GMC studies. Tim Davis is my kind of co-PI, and really a lot of the credit for what I'll talk about today really belongs to Ligia Liu. She was a great doctoral fellow working with me in Oxford for a number of years. She's now in Copenhagen, but really she came and I said, well, I've never done, MC before, so we need to learn about this together. And 4 years down the line, we have quite a few things to show. So it's been an exciting time. So I'd like to do a little bit today, explain obviously why it's interesting, and then show two case studies where we develop new formalism we see. And what is perhaps, I don't know if unique is right, but different, is that we look into star formation across the range of galaxies, not only the kind of spirals like the Milky Way, that people have been studying kind of forever, but also in the centers, for example, of early type galaxies, elliptical, zeros, and so on, where that are typically not the focus of star formation studies. So whenever I give a talk, I always start with this slide, no matter what the topic is, because that's what is driving me. When I say I want to understand galaxy formation, evolution, what it means to me is to understand this, the Hubble sequence, which is essentially a morphological sequence of galaxies. You have the most massive galaxies on the left with the oldest stars, the ellipticals and the zeros. And you can see they have quite old colors, red colors, so old star populations, very little cold gas and star formation, and are typically supported against gravity by pressure, right? So essentially the stars move not quite on random orbits, but on complicated orbits, a bit like a pendulum, and that's what prevents them from collapsing under gravity. On the right side, you have the lake-type galaxies or the spirals, and you can see that they have bluer colors, so more star formation, therefore necessarily cold gas. And obviously they're disk objects, right? If I was to rotate these around, you'd see they're quite flat like an old record and are supported against gravity by rotation, right? And so the key message from this figure as well is not is there the sequence, but galaxies, to take a bit of swipe at the high redshift community, or more than just a magnitude and a redshift, right? So they have lots of internal structure. So if you want to understand how they form, you need to somehow account for all this complexity. Of course, this does need to be understood in a cosmological context. So the name of the game is to explain how one goes from the faintest blob in the Hubble deep field, that are the farthest galaxies that we know of, at least until JWST flew and revealed potential objects farther away. But how we go from that to the sequence that I just mentioned via a sequence or a stage at cosmic noon, so 7-8 billion years ago, where we know galaxies were extremely gas-rich and turbulent. So, when I was at ANU doing my PhD, galaxy formation was very much thought as a purely hierarchical process, where essentially merging is the key. Small blobs merge, make big blobs merge, make humongous blobs, and at some point you call this a galaxy. Clearly, since now we know that gas is very important, the whole issue of gas accretion has become central, and I would say probably dominant now in understanding the galaxies that we see today. So the flow of gas into galaxies and its transformation into stars is very important. And often people would, instead of showing the Hubble sequence, they would show one of these stocks to justify one of these figures to justify their work. That's essentially the color magnitude relation, which is essentially an age mass relation, to zero order. And you can see that the most massive galaxies on the right are all red. These are essentially the ellipticals in the spiral here. And the mystery here is that if you burn the gas in this spiral slowly, like we know happen, you just consume star on typical timescales, the galaxy should move from the blue clouds to the red sequence fairly slowly. So there should be a lot of galaxies in the middle. But in this so-called green valley, there are very few galaxies there. That's why it's called a valley, right? And so that's the problem in, I guess, galaxy formation, how to explain that galaxies move very rapidly from here to there. It's not enough to just consume the gas at your typical rate. You need to get rid of it very quickly. That is referred to as star formation quenching. And really, you have two choices, right? Either you remove the gas, or somehow the gas remains there, but it's not turning into stars, right? And what I guess I'll try to address today is the second option of what if there is gas, how can it be prevented from turning into stars, essentially? So I guess that's a kind of justification. And just to illustrate this, here on the left, I put what's called the star formation law, but really it's not a law. It's not a law of physics. I would say it's a kind of parameterization of our ignorances that I would put this. What you have here on the x-axis is the amount of cold gas in a galaxy, and on the y-axis is the star formation rate, right? So the rate at which you turn this gas into stars. And most galaxies lie on a sequence, and this number is just the ratio, right? If you do mass divided by mass per year, you get a time scale. And this is telling you that for galaxies here, it would take you, a couple of giga years, 10 to the 9 years, to burn up all this gas. And clearly that isn't consistent with this green valley that I showed you. It also tells you that if you want to have galaxies forming stars all the way from redshift whatever to today, you need to replenish this gas, right? Because it would be consumed on a time scale of 2 gigayears. So the star formation law really is the reason I say it's a primary trace of our ignorance is, we don't observe H2, of course. We observe, CO typically is what I'll observe. And here we, of course, never observe a star formation rate. We observe so-called proxies, H alpha emission or near infrared emission and so on. So there's a bit of freedom in moving these axes around. And of course, we don't know the physics that dictates this, right? That's an observed plot. It's not, there's no physics in here, right? So of course, the physics come in this, which is the kind of gas cycle the cycle of gas in galaxies. Let's say you start with diffuse gas. At some point, gravity will manage to get hold of some of the overdensities. That's what gravity does, and then make the gas collapse. and you'll form these cores that will then turn into stars. You know, at some point, stars evolve. They might, you know, reject some of that gas through a planetary nebulous stage, or, you know, a type 2 supernova eject that gas, which will then go back in the interstellar medium, and we can start the cycle again with a more enriched material, right? So the stage that I'll talk about today myself is kind of this stage here, which I'm going to try to say, you know, the blobs that we see in the gas, are they in fact gravitationally bound, and will they therefore turn into stars at some point? Or is it that this gas actually is unable, you know, to collapse and form these stars, and therefore not turn into stars at all? So I'll be focusing today on this stage, and maybe talk with the study group later about the stages here, in fact. So, you know, why is it a good time to now study GMCs? Well, first, what are giant molecular clouds, right? We know this is where stars are forming. You know, they're kind of discrete gas clouds. And, you know, the mental picture we have is the kind of spherical cow model, right? It's a sphere of gas that is bound, gravitationally bound, and therefore will collapse. But of course, when you observe gas in galaxies, like I'll show today, we don't know a priori that this gas is self-gravitating, right? I'll just be identifying blobs. I'll call them clouds, but, you know, it shouldn't come with the whole baggage of what you think clouds are. They'll just be gas blobs, really. Their mass is typically 10 to the 4 to 10 to the 6, really. That's the largest number here. I should change. Size 5 to maybe 80 parsec, maybe 100 is typical. And dispersion is typically of a few kilometers per second. And lifetime, again, you know, probably like 3 to 10 is more what people would say. And I would argue formation destruction a little bit uncertain, although some people might disagree with this. And the reason that, you know, now is a good time to study this is because here's what ALMA is capable of, right? So ALMA is an interferometer in the south, has baselines up to 16 kilometers. So I put here 8.5, which is, you know, roughly can do in terms of angular resolution. And for the main transitions of CO, always the brightest lines, you know, in galaxies, this is the angular resolutions that you can reach, right? So this is quite amazing, right? I mean, in Oxford, we have a group building the first light instrument for the ELT. They've been talking about this for a decade, reaching this in the optical. But of course, with ALMA, this is quite trivial. This is routine to work at these angular resolutions. And if you want to study galaxies, not only the late type galaxies I talked about, but also early type galaxies, you need to reach the closest clusters of galaxies. And that means Virgo in the north, Fornax in the south, at the distance of, you know, 15, 16 megaparsec. And these angular resolutions translate to these physical resolutions. And you can see this allows you to spatially resolve the giant clouds that I mentioned about quite trivially, right? If the sizes are, you know, 5 to, let's say, 80 parsec, with these kinds of resolutions, we can spatially resolve them. And so that means we'll be studying individual clouds and galaxies all the way in the Virgo cluster, right? Where about this was done before, really only in the Milky Way and a few galaxies in the local group that are all very late type spirals, kind of, you know, barely any balls in the center, barely any spheroid. So this really opens a new realm of study of these objects. Just to give you an idea of what the basic ingredients I'll be talking about later, I'll be talking a lot about the so-called Larson's relation, and really it's a kind of fundamental plane of clouds. You know, if you're a Michael, you know the fundamental plane of galaxies, which is a relation between size, velocity dispersion, and mass. This is exactly the same for clouds. So luminosity is a proxy for mass, the size, let's say radius, and the line width is a measure of velocity dispersion. And the reason this is important is because for any gravitationally bound object, these are the key quantities, right? So if we think of high school physics, I said I wanted a whiteboard, right? If you have a planet going around the sun, right? You have gravity, GMM or R square would be compensated by, you know, centrifugal force. So you get that the mass is equal to, you know, V square R over G, right? That would be for a rotationally supported object. If you're supported by pressure, essentially random motion, essentially the same, but V, you know, is replaced by sigma, which is the velocity dispersion. There'll be a function in front of order 1, which is quite complicated. If you do stellar dynamics, that's called the asymmetric drift correction, or so on and so forth. So here that becomes, you know, sigma square R over G, with again some number in front of order 1. And so there are always three numbers that matter, right? Mass, velocity, dispersion, and size. And these plots plot two of these, versus each other. And that's the main kind of yardstick of cloud, kind of line with actually this one, size line with relations is typical one. These are two different projections. And what happened in the past is that people thought that these relations were essentially universal, right? All clouds in the Milky Way were kind of thought to be the same. And so these relations were thought to be universal. Again, that's very misleading. It's just because we never looked anywhere else before, right? So they were kind of universal for the Milky Way, in fact, because we just never probed any other environment. So in fact, over the last decade, it's been possible to probe a little bit beyond the Milky Way. And then people started to see some of these relations changing. So perhaps they were not universal after all. Perhaps these clouds actually cared about the environment, right? Which is a bit weird. If you think you're purely self-gravitating, you shouldn't care about what's around you. But clearly here they do. And so that provides a kind of justification to push these observations beyond, in fact, the late type galaxies in the Milky Way to other types of galaxies. And this is where really wisdom comes from. As I said, the original goal was just to measure supermassive black holes. Now we also study the GMCs. And what is unique compared to other people who study this is our entire spatial resolution, much, much, much higher than most people. So I'll show stuff today from under a parsec to essentially typically 10 or 20 parsec angular resolution. These are kind of postage stamps of the maps of the molecular gases from some of our objects. And I mentioned yesterday, some of our objects look a little bit like protoplanetary disk. This is in fact a molecular gas that's in the center of a giant radio galaxy. And that's the one I mentioned. For me, it looks very similar to H-Tau, for example, right? And for those of you who were at Josh's talk yesterday, you see spiral arms, you see rings, and maybe what you'd call truncations and so on, right? So we see the same range of behaviors that we are hearing about today at vastly different scales, right? These are typically about a kiloparsec across these disks. And reaching, well, anyway, the resolution, of course, is in terms of gravitational radars, maybe like several tens of thousands. But anyway, very annoying for us. A number of them, if you look, have little depressions in the center. And that's a killer for measuring the black hole masses, but that's actually the only place we care in the map, right? That's where the black hole signature would be. So that's a kind of killer for us. But anyway, it's interesting that these objects have all the structures we heard about yesterday. So another hint that something interesting is going on. This is actually the same maps, including some of later type galaxies from the FANGS project, plotted as a function of essentially stellar surface mass density. So that's how many stars are packed in the unifier, so a concentration. And here the Gini index, which is a measure of how contiguous the gas is. And you can see a clear correlation. And you can see that actually, this is essentially a proxy for morphological type, right? So spiral galaxies are here, elliptic galaxies are here. And you can see clearly that the ISM knows what kind of potential it's living in, right? It's much more discontinuous and blobby for the late types and quite smooth for the early types. And so, this hasn't been noticed before, but I think it's quite revealing, and it's telling you clearly that clouds do know and do care about the environment in which they live, right? So all of these smooth ones that look a bit like protoplanetary disks, in fact, are observed in the center of very big spheroids, while these ones here are quite messy and essentially pure disk galaxies. So we see, a systematic variation of the ISM property with the galaxy properties. And in fact, it turns out this goes all the way to the cloud scale. So you see here again, one of these Larson's relations, so size, line width. The black line is the Milky Way relation, and each of these circles is where the data of a given galaxy actually lies. So you can see a number of galaxies here, but a number also are quite different from the clouds in the Milky Way. And this is just another combination of these parameters. So let's see what happens now if instead of coloring these circles randomly, I actually colored them as a function of galaxy morphological type. You can see late types and pale colors are indeed, the clouds are indeed similar to those in the Milky Way. But as I move away to early type galaxies, you see a systematic deviation, right? So again, it seems that not only the large scale interstellar medium knows about its environment, but the clouds themselves that were thought to be purely self-gravitating actually know what kind of galaxy they live in, and they react accordingly, right? Their gravitational equilibrium, if you want, is affected by the potential in which they live. And that, I think, hadn't been realized because, as I said, this relation was thought to be pretty universal. And so we set out in Wisdom really to try to elucidate why that might be. And the first galaxy I'm going to talk about is one of these big galaxies. This is a lenticular S0 galaxy in the Virgo cluster. This is a typical optical picture. This is a massage Hubble Space Telescope picture in the inner parts, and you can see there's a lot of dust in the center that seem to lie in a beautiful disk. And if you want to measure black hole masses, that's ideal because it's telling you there'd be a lot of molecular gas with stuff moving on circles. So you can actually, again, use your high school physics just to infer the black hole mass by measuring essentially this curve, right? Now, the molecular gas is indeed there. So this is the map of the molecular gas obtained from ALMA. Beautiful velocity field, so very regular. But you can see here several blobs, right, that I'll call clouds. But as I said, we don't know a priori that all these blobs are self-gravitating. And we'll probe each of those in a spatially resolved manner because we actually spatially resolve most of those given observations. So this is the same map where the clouds that our algorithm has identified have been essentially overlaid. The blue ellipses are the ones that are spatially resolved. And so we can measure, size, line width, and mass of each of those blobs. I'll go quickly, but essentially one thing that is surprising in this galaxy is that the velocity dispersions tend to be much higher than usual. And so the question is, why is that? And let's look a bit more detail. Let's go back to this, and now I'll replace this velocity field of the galaxy. So this is the large scale velocity field in colors, so iso velocity contours. And here I show you another velocity field, but this isn't a high redshift galaxy. This is typically what the velocity field of galaxy at redshift 1 or 2 looks like. This is actually the velocity field of a single cloud in this galaxy, right? And what you can see is that this cloud is in rotation, right? So its line width that you measure isn't actually kind of a velocity dispersion. It's not turbulence. It's not random motion. The line width is just essentially twice the rotation velocity, right? If some of you are familiar with, whatever H1 observation galaxies, you get these thing called integrated profile, you get this thing, these double horn profile, and the width of this, nobody would call this turbulence or random motion. This is just twice the rotation velocity of the galaxy. And so, in fact, these clouds are a little bit like this, that essentially the line width is not due to turbulence. So it shouldn't be plugged in here because dynamically it isn't a random motion. It's just bulk rotation of the cloud. And that's why we were measuring such large line widths. So what we have to do really, if you want to measure the turbulent component, is subtract this rotation and just measure essentially the width that you're left with. So what we do is at every point on the sky, we have a spectrum. We shift them so that essentially the mean velocity is 0 everywhere. And then we looked at the line width that is left. And that is the true measure of turbulence in these objects. That's the sigma that needs to go in this relation here. And then the trick is, what do you do with the rest? And that's where we fold in the influence of the external galaxy on these clouds. Okay, so this is something called the Virial theorem, which applies to all gravitationally bound object, right? A satellite around the Earth, the Sun, electrostellar structure for a few years, and I call this kind of the origin of life. But for the Sun, this is why the Sun is so stable. Essentially, the sunshine loses energy, contracts a bit, so heats up, so expands a little bit, and so on. Right? So this is essentially the Virial theorem. So the Virial theorem always states that, what is it, 2k plus u equals 0, where this is the kinetic energy term, and this is the gravitational potential term. I'll put a V on that, right? And that applies to all bound objects. And so here, if you ignore the factor of 3, that is twice 1/2 mv squared, right? So that's kinetic energy, 1/2 mv squared. So twice this is this term. And that's the gravitational potential energy, gm squared over I, right? So if this is true, then the sum of these two sums should be 0. right? And that's a cloud that's in equilibrium, and happily will be long-lived. And this is the conventional Virial theorem, where the sigma is a true turbulent term. It's just random motion. A cloud that's supported against gravity by random motion. So the kinetic energy should compensate gravity for the cloud to be in equilibrium. But now for this cloud, I've shown you that the clouds are in rotation, and we believe that rotation is essentially forced by the potential of the galaxy, right? So if you think about it, if you're in an area where gravity is very strong and you're rotating around a galaxy, the center is here, you're moving on orbits, let's say the rotation curve of the galaxy is flat, all these clouds move at the same velocity. If you're a little bit farther, you will lag behind because you have longer to go around, right? So locally, essentially, these ones are kind of moving like this. The ones that farther radius will go, and that's called shear, right? So essentially, if I'm rotating around the galaxy, this arm is lagging behind, right? So I'm getting, actually it's easier to go the other way around, but yeah, right? I'm getting stretched by shear. And this is what these terms now are. This is a equilibrium in the vertical direction. So the vertical velocity dispersion must compensate gravity. That's the scale of height in Z. The potential is in here. You don't need to, and this is the movements in the plane, so radial and tangential. This is again related to the potential. It's the tidal force, right? So you also, one side of me is being put stronger by the galaxy than the other because one side is closer, right? And this is essentially the Coriolis term that is stretching you. So this is what the new Virial theorem is that folds in the effects of the galaxy. However, this is absolutely useless because I cannot measure any of these three terms, right? Because all I see is movements along the line of sight. So this is very nice theoretically, but absolutely useless in practice. These terms here I know just from the rotation of the molecular gas. I know what the potential of the galaxy is. So it turns out, though, if you play a bit with the maths, that you can relate all of these terms to observables. So essentially, the one that you observe is a combination of this true purely turbulent term and some of the rotation, and you can, it turns out, relate all of these terms to things that you can actually observe. And if you do this, then you get this modified Virial theorem, which looks just like the classical one, except that here sigma we call sigma effective, and that's a measurement that actually is an observable. So this is, GS stands for gradient subtracted. It means the cloud where we remove the rotation. This is the actual observed one, the one with the rotation removed again, the inclination of the galaxy, and these are these terms that are due to the potential that we can actually know observationally as well, just from the rotation curve that we measure from the same observation. So this then is a new criterion, right, to decide if these clouds are bound in the presence of this external potential of the galaxy itself. And we can apply this to our data. Everything there is an observable or something you can measure. So I'm not quite sure. Oh. So we can look at many of these. Larson's relation. This is the more interesting plot. This is the ratio of the observed mass. Well, okay, luminous mass. You just see how much gas there is, and this is the virial mass. So this is a measurement of what we call the virial parameter alpha, which is the ratio of a dynamical mass to a gaseous mass. So this is literally what we observe, how much CO there is. This dynamical mass is just what is predicted if it's in equilibrium. So it's, V square R over G over M gas. And so obviously, if you're this, actually I should put a sigma here. If the turbulence is too large, you're going to blow yourself apart, right, compared to your actual mass. I think the cloud cannot keep itself together because there's too much random motion. So this ratio will be bigger than 1. If the random motions are small and the mass is too big, then the cloud will collapse, right? So it cannot support itself against gravity. And just to link this to the Virial theorem I mentioned before, you can see that if I just multiply this by M gas on both sides, I have M gas, sigma square over M gas square. So I have G over R, right? This is just equal. And that actually is 2K over V, right? 2 times kinetic over potential. So it's essentially deciding which of these two terms dominate. If they're equal, alpha is 1, I lie on this straight line and my clouds should be gravitationally bound. If the kinetic term is too large, then I'm above the line and these clouds cannot hold themselves together and should be transient, right? They will dissipate over time. If the dots are below, it means alpha is smaller than 1 and then they should collapse very quickly, right? They're out of equilibrium. And this is the plot that one gets if I use just the observed velocity dispersion. So they're all above the line. Alpha is about 4 on average. So it's telling you that these clouds I've been calling are not clouds at all. They're just blobs of gas that should dissipate very quickly, right? If I were to take another picture millions of years later, it's going to look totally different, right? Now, but of course, I argued that these dispersions are too high. You know, they're not turbulent. So I really need to remove the rotation. If I remove the rotation, now the picture changes quite drastically. All the clouds seem to have alpha of 1. And then I would conclude that all these clouds are in equilibrium and long-lived, right? Well, I'm not finished because I need to put back the rotation in the appropriate manner using this effective kind of dispersion that I talked about. And this is really what our formalism does. And now you can see the picture is kind of mixed. Some clouds probably are bound, but on average, it's kind of marginal. Usually, actually, an alpha of 2 is what people will use. So, and we get on average of 2. So that means these clouds are just kind of marginally bound. You know, they're kind of just about hanging together, kind of by the skin of their teeth, right? So the conclusion we get is quite different than if we had used just the observations kind of naively, right? So the question is, what does it say about this galaxy, the fact that these clouds are just marginally bound? Well, it turns out when you look at these clouds, all the clouds fill their tidal radius. If you measure for mass the place in the galaxy, you can measure the tidal radius, and all these clouds fill this. So that it does seem consistent with the fact that they're barely hanging together. So, okay, let me skip this. But anyway, we have a formalism that allows us to calculate like the extra thing you get from the galaxy. And it turns out the model that we have predicts the observation perfectly. This is the distribution of alphas that the model predicts, an average of 2, and this is the observed one. So it's clearly much broader here because of observational error. But essentially, the average is exactly the same. And if these clouds are at the large scale potential of the galaxy, then in fact the prediction is that these clouds are as large as they can be before kind of blowing themselves up, essentially, so kind of just hanging together. And of course, if that's the case, then maybe this gas is not going to collapse and form stars. And we know that in early type galaxies, the star formation efficiency, the ability to form, is much lower than in spirals. So the star formation law that I mentioned before is only observed in disks. And we know that in early type galaxies, all the data are quite offset. So this is another way maybe one can quench star formation, is by actually not removing the gas at all, but preventing this gas from essentially becoming bound, collapsing and forming stars. And that seems to be the case here, because this gas is embedded in this very, very large, massive, and centrally concentrated galaxy. But this whole approach also suggests something very, very basic about saying how clouds might form, right? So this is the galaxy I've talked about. The colors is the large scale velocity field. And I didn't say what the arrows were before. So the arrows are actually the projected angular momentum of each cloud individually. Okay, so if you remember undergraduate physics right-hand rule, right? So this cloud is rotating like this. So the angular momentum is pointing down. So that's the arrow. In fact, this is one of those clouds here. And you can see in this case, all the arrows are aligned with the colored lines. Okay, so that means that the internal rotation of the clouds is in the same direction as their orbital thing, right? So essentially, if I'm going around the galaxy, this is where somebody once challenged me to, that we had the challenge is dance your thesis. Well, now I'm going to dance my research result, right? As I go around the galaxy, I need to rotate in the same direction, right? And that, of course, is exactly what you expect based on dissipation while conserving angular momentum, right? But the next galaxy I'm going to talk about, so in the galaxy first, essentially the number of counter-rotating clouds, and it's quite difficult to do this. You have to go like this or rotate in the other direction. It's actually not trivial. Here, only 1% of the clouds are retrograde. Okay, so that is quite consistent with these clouds just collapsing under gravity, you know. But in this next galaxy I'm going to talk about, how the clouds are going one way, how the clouds are going the other way. Their internal spin is not aligned with their orbital spin. So what that suggests to me is that these clouds had a much more violent history. And for that, we can actually learn lessons from the solar system, right? In the solar system, it's the same. The planets going around the sun, their internal spin is all aligned with their orbital angular momentum, right? Except a few. The Earth, of course, is tilted by 23 degrees. And usually the explanation for this is there was a huge collision that created the moon, right? And that tilted the spin axis of the Earth. In fact, Uranus is at 90 degrees. So clearly, again, a very violent event. So I think doing this very simple statistic, if you want, of retrograde versus prograde cloud could tell you a lot about whether collisions are important in the formation and evolution of the clouds. Because you know that's a possibility, right? There are many clouds going around. They can collide with each other. This one tells me this process is probably not very important. But in this galaxy, it probably is dominant, right? Collisions are very important. If they were not, you wouldn't end up with these clouds being largely misaligned. So I think this is a very easy diagnostic that's potentially very powerful. And I've now been inciting a number of simulators to look into this in their simulations and see if there's any truth in my kind of gut feeling here. But I think that's quite easy because measuring just the alignment of the clouds is trivial. It's not very difficult, right? In fact, that doesn't even require as high angular resolution as I've been using so far. So that's just a kind of idea we're throwing around. So I want to talk very about galaxy. So this is actually our winner in terms of resolution. So maybe usually I challenge people, can you guess what the spatial resolution is in this object? And experienced radio astronomers know that the beam there is always shown in the bottom left corner of the map, and it is here. It's actually this tiny black dot there. So that's our resolution element. And in this case, it's actually less than 1 parsec. So in fact, this whole thing is just about 100 parsec across. And you know, if you remember, the distance from the sun to the nearest star is just over 1 parsec. So if we were looking at stars, we would actually be looking and seeing and measuring the velocity of every star in this galaxy separately, right? So that's how good the resolution is. And the reason this was important, you can see here, actually we measured the mass of the black hole in this galaxy, which is a dwarf galaxy, and got a so-called nearly intermediate mass black hole, which is the next challenge in these black hole mass measurements to go to low black hole masses. So we were able to measure a black hole mass of less than 1 million with those data, but that's not what I talk about today. Today I want to talk about, you know, if you go and measure clumps in this galaxy, what their properties are. I hopefully won't keep calling them clouds because clearly this is essentially the size of a single cloud, the whole map, but we're going to identify, you know, hundreds and hundreds of smaller clumps in the object. And remember, that's the object where half of these clumps had a spin that was retrograde compared to the large scale rotation of the galaxy. So this is again the Larson relation in this galaxy, so line width size. This is what happens in the very middle. And okay, you get something halfway between the Milky Way disk and the center of the Milky Way. The CMZ is a special region, central molecular zone of the Milky Way. And you know, the red dashed line is the model I'll talk about in a minute. And you can see it's a parable representation of the data. And in fact, we know the model shouldn't apply to the inner parts. However, outside of the very middle of this galaxy, we measure hundreds of structures, and the prediction of our model seems to be very good. You know, this red dashed line follows both the data point, and this model predicts the 0 point, the slope, and the turnover with no free parameter. So it's great, you know, success. So let's look what this model entails. I'm always told, you know, we're not supposed to show formula in talks, but I'll try to say in a few words what this model entails. It's a very simple back of the envelope model. We essentially see any two clouds that come within 1 tidal radius of each other, they merge, okay? And the velocity of this merging, this collision, is specified just by the shear, which is the differential rotation of the galaxy, which because we know the rotation curve. So that's good. And well, yeah, that allows us to calculate a rate at which these collisions occur, and therefore, the energy dissipation due to this collision, and so on. So, and the nice thing is, for example, so that's the tidal radius, gravitational constant, mass of the cloud. A is Oort constant A. So if you know the rotation curve, A. A is the Oort constant that characterizes shear. That's why it's relevant. Here, you get the collision rate, and a typical length scale naturally arises in the problem. And the nice thing is all of these key quantities do not really depend on the clouds. This is the surface density of the disk, so how many solar masses per parsec square of gas you have. And this is Oort constant A again, which just depends on the large scale rotation curve. A typical mass comes out, again, only depends on the properties of the disk. And if you equate the energy that you dissipate for these collisions, right, the speed of the collision, the mass involved, and the rate, then if you equate this to the kind of typical energy you require in the turbulent cascade, the size line width relation comes out, which is this red dashed line here. And so we get an analytic prediction just with a few lines of algebra of this line width relation, which again only depends on the large scale properties of the galaxy, so gravitational constant, surface density, or constant A. And you can see that below this typical length scale, it goes as the size of the clouds to the 1/3. Above the length scale, you don't have energy input anymore, and so that just becomes a constant. And that's exactly the prediction that I showed here, which fits the data perfectly. So a very simple back of the envelope collision model seems to reproduce the properties of the cloud in this galaxy. And it's nice because it's the galaxy where half the clouds were rotating the wrong way around. So it was kind of telling us that, telling us that these collisions are important in this galaxy. So it turns out you can make a number of predictions. It's probably a bit small for you to see, but in all of these plots, you see essentially blue curves and red curves. And in the outer parts of the galaxy where we think our model applies, one is observation, the other is model prediction, and they always agree perfectly, essentially. The predicted mass and the observed mass of the clouds, these are the energy injection rate, essentially, and dissipation rate, and the size of the clumps, and so on. So all of this seems to fit very well in the region of the galaxy where we think this model applies. What is perhaps even more interesting is that we can apply this model to high-redshift galaxies, and it seems to fit as well, again, with no free parameters. So in colors here, you get clumps measured in high-redshift galaxies, all in these systems. They all have strong lenses, so that's why you can actually resolve clumps, right? So normally you wouldn't be able to do it, but because of gravitational lensing, strong lensing, you can do it. So you got the properties of the clumps in these galaxies, along with the prediction of our model, and you can see in every case, the model seems to reproduce the data very well. So we're very excited by this, right? It's a trivial, very simple model, but it seems to apply to these higher redshift objects, which we know have big clumps and are very gas rich, and therefore where we think collisions may well be very important. So I wanted to say, I'm going to skip this. I wanted to say a few words about, if we want to really relate this to quenching, we need to relate the properties of gas with the amount of star formation that we see. And so we need to have measurements of star formation rates as well. The problem, of course, is I've told you we're working at kind of 0.05 to 0.1 arc-second resolution. So the challenge is to have what we call a star formation rate indicator at such high angular resolution. And there are just really many of those, there just aren't many of those around, right? If you think about H-alpha, which is a workhorse, typically done with ground-based telescope, that would be about 1 arc-second resolution, typically. If you want to do infrared, that's even worse, right? Typically several arc-seconds, if not more. So really the only thing that we could do at similar resolutions, I think, is radio continuum, especially free emission from the H2 region. And that's what we're trying to do now. And here's one example of a galaxy where I overlay CO and free emission. But that's really where our project is going for the future. That's another example where we use H-alpha, but at kind of arc-second ground base. resolution with an instrument called CTEL, the CFHD. But that's the next step now, is to really relate in a spatially resolved manner the properties of the cloud that we've measured with the star formation rate that comes out, right? At the moment, we know in early type galaxies, the star formation efficiency is lower, but only in a kind of global manner. Nobody has ever resolved this spatially. So that's the next step for us. And we've started to do this, but you know, it's mostly in the future. I think I'll stop here. I hope I've convinced you that ALMA is an amazing instrument that allows you to probe really in a spatially resolved way, you know, the key scales for star formation, which is the scale of the clouds where we know star formation takes place. We seem to see various reasons why the properties of clouds do depend on their environment, right? If they're in of a very massive galaxy, or if collisions are important, you'll get different behaviors than the kind of nice isolated gravitating clouds that you get in the neighborhood, where you're quite far from the center, and they're, you know, it's not too crowded, right? It's not the kind of CBD, you're way out in the suburbs. But you know, just like people, clouds behave differently in the suburbs and the CBD, I guess. So I'll stop here. Thank you.
Very much. Are there any questions?
Early on, you showed the image with the disks as functions of stellar density.
Yep.
I was wondering about is that these beautiful disks in early type galaxies. Yeah, like it sort of looks backwards in the sense that you've got rich disks in early type galaxies, and then you've got fragmented low density disks in the spiral galaxies. So what's going on there?
One thing I should say, maybe these are certainly smaller than those in terms of sector. Here, these are not all on the same like scale in kiloparsecs. So these are about the kiloparsec in size. These would be much bigger, but nevertheless, they're more blobby. I think what really happens is what people call morphological quenching, which is essentially that the external potential just stabilizes things. We know that's always been the case on large scale, but seems true on smaller scales. In fact, more and more likely, maybe this is not surprising, because we know that the molecular gas typically follows the stars in terms of surface brightness profile. And of course, the surface brightness profiles of early type galaxies is very smooth, but their surface brightness distribution is very smooth. So perhaps it's not surprising that the gas is smooth as well. The way people usually explain this is that they say that to convert from atomic gas to molecular gas is probably a pressure criterion. And so that follows essentially the gravitational potential in the disk. So if that's, you know, very smooth, then I guess you get smooth molecular gas. But I haven't given this much thought. Certainly nobody had, you know, noticed this before, and that's, you know, that result is not even a year old, so we haven't fully digested it. But it's certainly, for me, it's telling me that this morphological quenching idea that simulators have been talking about for a while probably has some truth in it, which is that the external potential just kind of stabilizes everything.
Right. And your clumps in those regular disks, because they've got a lot of shear, they're not collapsing to form stars.
Well,
not much.
Yeah, so that would be my take on it. You can think of it a little bit, sorry to go back to the board. I like to think of it in terms of Q, the stability parameter, and I was asking questions of it yesterday. You know, Q goes to kappa, you know, the cyclic frequency, sigma, the velocity dispersion over capital sigma, which is the surface density. And if you think about this galaxy, you know, sigma is always about 8 kilometers per second. We don't know why, but it's essentially a constant. It's the same everywhere. Kappa goes as 1 over r. So the outer parts of the disk is always very small and very flat, right? 1 over curve goes like this, and in this part. So Q is really purely a surface density criterion. And in fact, when people look where star formation takes place, they often find that you can use a surface density threshold or a Q threshold. It gives you the same answer. So I would argue it's expected. But in an early type galaxies in the center, we don't know what sigma is. And because you're in the inner parts, kappa can be very high. So if kappa is high, you can have quite high surface densities while keeping Q high, right? And obviously what matters is whether Q is bigger or equal to 1. So I think in early type galaxies, just from a kind of stability perspective, it's possible to have quite high surface mass densities while still keeping Q quite high, because kappa can be quite high and sigma we don't really know.
So you could fit your AGN in the center of these things, but not necessarily have star formation accompany. And it wouldn't have anything to do with AGN feedback necessarily.
That's
just be with the nature of the potential.
Yeah, yeah. In fact, this galaxy here, the one I pointed out, looks like HL tau. This is a giant radio galaxy. Yeah, humongous jets coming out of this. So clearly, the fact that there is a very powerful AGN is not affecting this at all. And this has a perfect velocity field. Yesterday we heard about looking for kinks. This galaxy is just absolutely amazing. The velocity field. If you show it to somebody, they think it's a textbook model that you're showing.
Control Darren, so sleep there.
Yeah, over these 2-hour schedules with him.
Just curious about your, so these molecular clouds come on now. So if you do the same analysis on the Milky Way's molecular clouds, most of the things there are something. The efficiency of stuff.
Well, okay, depends what you mean by low. My understanding of so we haven't done it, but I think my guess is near the sun that wouldn't be relevant, because essentially shear is not very important, and the gravitational potential. But in the central molecular zone, which is, this zone in the middle of the Milky Way, which is very gas rich and very low star formation efficiency. So it's a mystery. The central molecular zone is full of gas, but essentially no star formation. So in fact, a lot of the drive for this is an analogy with the central molecular zone in the Milky Way. And I think that's right, probably very similar conditions. So we haven't applied this formalism to those clouds. Whether we could or not, I'm not sure, but yeah, we're talking a lot to the Milky Way people who focus on the central molecular zone. So Kara Battersby and so on. I think one issue, of course, with the Milky Way is if you want to apply this, you need to know the circular velocity curve very accurately in the inner parts. And I suspect that's not well known in the Milky Way, right? The inner parts is very difficult. So.
Related to that, so like you mentioned some of these is dark matter any like importance on scales?
Not on the scale of the clouds, for sure. Large scales it might be, but that's folded in, the circular velocity curve as it's all the mass, right? Whether it's dark or luminous or whatever. So in a sense, it's included in there. Yeah. But what's interesting, in this one galaxy where I argued the clouds are marginally bound, I forget if we put it on the paper, we calculated how much stellar mass there is within the volume of a cloud. And it turns out there's 6 times more on average stellar mass than molecular gas mass within a single cloud. That's how dense these galaxies are in the inner parts. So in a sense, I would argue it's crazy to think that the external galaxy has no effect on the clouds, right? If this mass is uniformly distributed, it would not create any force, right? So it would be irrelevant. But of course, it's varying very rapidly in the inner parts of the galaxy, right? So the density profile is very steep. And so it's entirely normal, I would think, that you need to fold in this potential to explain the clouds, because after all, there's 6 times more mass in a given volume due to the stars of the galaxy than to the molecular gas of the cloud itself. So, I didn't expect this, but we just made the plot and said, whoa. So, yeah.
The earlier plots you show you have this grounded plot of clouds.
I'm not sure you mean. Yes.
There was a ring of lots of clouds. So this is showing.
Oh, yeah. Sorry, I've lost my cursor for some reason. I don't have cursors, but I know which plot one. This one.
So, because of the ellipses, it looks like I'm not sure how, like, for some of them, you can divide it into plots.
Okay.
Good criteria.
So 2 comments. The first one, of course, is we identify the cloud in 3D, not 3 spatial dimension, but x, y, and velocity, which is what we observe. So this is a 2D plot. So some ellipses might not seem realistic because you could have several blobs along the line of sight. Some of the material you may not be associated with the cloud. So that's one comment. So in 3D, it would be a better match. But I think this is actually the weakest step of the whole process. And that's the one I want most, is identifying the clouds. Once you've decided what is a cloud, measuring its size, mass, and dispersion is actually pretty easy. But there is some arbitrariness. And we use a code called cprops, which has a number of parameters you can play with. We think we improved it, made it slightly less arbitrary. But there is, the issue is, call it a clump or a cloud. How much does it need to stick above the background, right? And that you pretty much put in by hand. So there is arbitrariness there. And what we do is we run everything for several reasonable parameter combination, and we make sure that the results don't change significantly, essentially.
Because I was wondering if some of these rotation laws were just because of nothing to.
Yeah, in fact, what we haven't done, but one person keeps telling us to do, which I agree with, is just to put on essentially random ellipses and make sure that we get something different. Right?